Hello class, today we're looking at sums of series. So remember, a series is just a sequence when we've got a bunch of plus signs, and we're going to be looking today at some shortcut rules to help us add them all up. And then also what happens when we have an infinite series, infinite geometric series. So first we have a short rule for finding the sum of a finite arithmetic series. So finite because it stops, arithmetic because you have some kind of adding, some kind of common difference, right? A constant rate of change. So my formula is n times, in parentheses, f sub 1 plus f sub n all over 2. We need to talk about what all these things are. So my f of 1 stands for my first term. And it's not necessarily 1. Not, because we know terms, we could start counting with 0. We could say we only want to add the third through the 10th terms. So not necessarily f of 1. And then this is my last term. So I have to find my first term, my last term, add them together, divide by 2. You're basically like finding the average, and then the n is the number of terms. And be really careful. If you start at 1, end with 10, it's super easy. You're just adding 10 terms. But if you start at 0, or if you go from like 3 to 12, it can get weird. So number of terms we are adding. Next formula is for sum of a finite geometric series. So geometric because you're multiplying each time. And remember, that's going to look like something, it's going to look like an exponential function, right? Where your variable is your exponent, where you've got your start, your growth factor, and your exponent. It looks something like that when you're looking at it in sigma notation. And the way we find that is we got our first term, so it's going to be f of 1. And then we've got times this giant fraction, 1 minus r to the nth power over 1 minus r. And so n, again, is going to be the number of terms. F sub 1 is my first term, not necessarily 1. And then r is going to be, I don't think I want to write a minus sign there. It looks kind of like a minus sign. Maybe we'll just write it as r is. R is the growth factor. So that's the multiplier, the one we're multiplying by every single time. Our ratio, our common ratio. So sum of infinite geometric series. So only if our rate of change, it's not ratio, right? Our ratio, our growth factor, I'll multiply. Only if our multiplier is less than 1 can we even find the sum. So if our multiplier is greater than 1, if the growth factor is greater than 1, then that means it just keeps growing and growing and growing and get bigger and bigger and bigger. And so it's not really going to have any kind of sum. So we say it has no sum. Only if we're multiplying by something less than 1 do we get close to having that sum. And that's because we're just adding like little tiny parts of something. And these are absolute values, so they could be negative or positive. All right, so if we can find the sum, the formula is really simple. It's our first term divided by 1 minus r. So again, r is my growth factor, and f sub 1 is my first term. So we're writing, the notation's a little bit different. I'm not writing f of 1 because I'm trying to show you that this is the first term. It's something different. So for our first example here, we got 11 plus 8 plus 5 plus 2 plus dot, 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 dot. And we want to sum the first 11 terms. So let's first write out what we're doing. So we're starting, we have to decide, do we want to start with 1 or with 0. So most of you are probably going to choose to start with 1. So if I start with 1, I would write it at equals 1. I'd go to 11. And then we would figure out our formula. We start with 11 plus each time to get from one term to the next, we're adding 3. So it's going to be 3 times n minus 1. That's what we're doing, okay? So what I really need for this formula, though, if I look up at my formula, I need my number of terms, I need my first term, my last term, the divide by 2 part. I don't really have to write it in that summation notation. So let's go through and let's write everything down. So I have my first term. My first term is 11. My last term. That's where I really need this formula, right? So in order to use my formula and find the last term, let's go ahead and write over here f. I want to change my notation a little bit. So my first term ends up being f of 1, which is 11. My last term is going to be my f of 11, which is 11 plus 3 times 11 minus 1, that's 10. So that one's going to be, let's see, 11. Oh, wait. I'm not adding, I'm subtracting. That could have been bad. Minus here. It's going down by 3 each time. It's a good thing I had my notes handy. Minus. Okay. No wonder it did not look like we did in class. So 11 minus 30 is going to be negative 19. That sounds more familiar. And then what else do we need? And our number of terms is just 11. Okay, so now I set up my formula. My sum of my first 11 terms, I could just write an equals here too. That just means the sum of my first 11 terms as well is going to be 11 times first term, 11, plus last term, negative 19, divided by 2. So 11 plus negative 19 is negative 8 divided by 2, so negative 4. 11 times negative 4 is going to be a negative 44. I'm kind of running into the next problem here. All right, so it's formulas to memorize, right? But then we're just plugging things in. So I had to find my first term. I had to find my last term. And then I had to identify the 11, right? And then we're just putting everything in our formula. So the next one I can tell is not arithmetic. Like that first one, we could tell we were adding the negative 3 each time. This one is not arithmetic. It is geometric. And that's because my variable is the exponent. So if I want to do my finite geometric series, first I need to find my first term. So we've got to find our f of 1. So f of 1 is going to be 4 times 3 to the 1 minus 1 power. So 3 to the 1 minus 1 power, that's 3 to the 0th power. So 3 to the 0th is 1. Anything to the 0 power is 1. If it's in parentheses, it includes the negative. It's going to make it a positive 1, and that's just going to be 4. Our r here is the part that's being raised to the power, because if I think about like 3 being raised to, say, the 4th power, that means I'm multiplying 3 4 different times. So that's my multiplier. It's how I'm growing. I'm growing by a factor of 3 each time. So r's going to be that 3. And then my number of terms is going to be 16. So now I want to find my sum of the first 16 terms. We can just write sum equals, or you could write 16. But that's going to be, let's see, 4 times 1 minus 3 to the, let's see, nth power is 16th power over 1 minus 3. And you should get, and this is a little tricky, this is definitely like a can use your calculator, you should get 86093,440. And be really careful. What I was showing students is you really need parentheses around this one divided by parentheses around this one. And that's going to help you. Next one, I have an infinite, right? It goes to infinity, infinite geometric series. My r is equal to 0.8, and that is going to be less than 1, so we're good to go there. We can find our sum. And so my formula says I need my first term. Well, in this case, it's going to be f of 1. So 5 times 0.8 to the 1 minus 1 power. That's going to be a 0 power. It's just going to be a 5 times 1, which is just 5. And I need r, and r is 0.8. And then to find my sum of the infinite series, then it is f1, which is 5 over 1 minus 0.8. So 5 divided by 0.2, which is, I don't know why I made the 2 so weird. Let's fix that. It almost looks like an exponent or something. 5 divided by 0.2, or 2/10, and so we should get 25. So now we're on the back here. Find the sums of the infinite geometric series. And that's for number 1, right? So we need, make sure you have your f of 1, make sure you have your r. So my f of 1, my first term here, well, let's go through and find it. So f of 1 is going to equal 6 times 0.6 to the 1 minus 1 power. 1 minus 1 is 0 power again. That's going to be just 6 times 1 or 6. And then my r is 0.6. So remember, check your r value. The absolute value of 0.6 is less than 1, so we're good to go. We can find our sum. So this is a good spot. Go ahead and pause, and you could try these on your own, and then you could go back and unpause it. So sum is going to equal, and I could just write s equals, it looks kind of awkward to have that giant equal sign over there. So let's write s equals 6 over 1 minus 0.6. Again, if you're dividing this out on a calculator, you're going to have parentheses around the 1 minus 0.6, and it should equal 15. For b, we've got to figure out, let's see, we've got our first term. So f of 1 is going to equal 1. And then what is our multiplier? 1 times 2/3 would be 2/3. Let's see, does that work again? 2/3 times 2/3 is 4/9. We've also got a sign switching thing. So r is going to be a negative 2/3. So I have enough information now because r, the absolute value of 2/3 is less than 1. We're good to go. Absolute value of negative 2/3 is just 2/3. So then my sum is going to equal 1 over 1 minus a negative 2/3, which means we're going to be adding. So 1 and then 3/3 plus 2/3 would be like a 5/3. 1 divided by 5/3 is 1 times 3/5. So it should just be 3/5, which is also 0.6. So nice when we can do something with fraction work though. For C, let's see, it looks like if we put in 1, we get a 1 minus 1, 0 thing going on again here. So my f of 1 is just going to be 4, or no, 0.4. And then my r is equal to 2. Oh, but wait, 2 is too big, right? That's greater than 1, so there would be no sum here. So it's actually diverging instead. It's not adding little tinier and tinier bits each time. It's multiplying and adding bigger and bigger pieces each time. So it's never going to converge. It's going to diverge. There's no sum. Okay, so for the next two, I feel like we did something different on 3 in class. So I'm going to have to think about that for a minute. But we're doing 2 first anyway, so it's fine. So what I notice here is that this is arithmetic. So the other ones I had something in the exponent. This one I'm not. It's 9 plus 3i. So I just keep adding more and more 3's every single time. It's going to be like a 3 times 2 or a 3 times 3 or a 3 times 4. So each time I'm adding another 3 basically. So for this one, remember that formula. It's going to be n first term plus last term all over 2. So let's go ahead and fix that. So I want to make this, let's see, n is going to be 15. And I got to find my first term. So my first term is f of 1. So that's going to be 9 plus 3 times 1, which is 9 plus 3, which is 12. Okay. Then I want to find my last term. That's f of 15. So that's going to be 9 plus 3 times 15. So 9 plus 45, which is 54. And we already said n was 15, so now we've got everything we need. So 15, 12 plus 15, or no, 12 plus 54. Almost wrote the wrong thing. 12 plus 54 all over 2. And that's going to be 495. So again, be really careful with your parentheses, your order of operations. So this last one, I think what we did in class is we just changed it around a little bit and played with it. And we said, what if this is from I equals 0 to 6? Let's just use those instead and play around with it. And then what would happen? And we tried this one a couple different ways is what we did. And I think it really works well for this. So if I have I equals 0 to 6 of 3 times 4 to the I minus 1 power, well, it gets a little bit weird, right? Because first of all, my first term is 0. So 3 times 4 to the negative 1 power means 3 times 1/4, which is 3/4. The next thing that's weird is n is not going to be 6 because I'm starting at 0 and including it. I'm adding the 0 term, the first term, the second term, the third term, the fourth term, the fifth term, the sixth term. So it actually ends up being 7 terms. My r here is the 4. And then that was enough information. I don't think we actually got a number out of this. We could really quick though. So 3/4, 1 minus, let's see, 4 to the 7th power over 1 minus 4. I'm going to have to do this really quickly on my calculator. And then I would like to do one more thing and just think about how n changes. So like I said, I got to do this on my calculator really quick. I'm definitely worried though about the number of terms because I think that can be one of those things that we miss. So my numerator, so now I have 3/4 times negative 16,383, and then we're dividing by negative 3. So I'm going to press equals, divide by negative 3, which is a beautiful whole number, 5461. And then let's multiply again. I'm just going to go to decimals at this point. So 4095.75 is what I come up with. Hopefully that's right. Like I said, I'm just kind of doing this off the top of my head. The really big thing I'm worried about is this, and using a phone calculator is not ideal. So if I did something different, let's say I had something that started at I equals 2 and ended at 6. How many terms would we have then? And it's really tempting to say, well, 6 minus 2 is 4. There's 4 terms. But remember, you have your second term, third term, fourth term, fifth term, and sixth term. It ends up being 5 terms that we're adding. And so n equals 5. So be really careful. If this doesn't start at 1, then you're going to have to like subtract and then basically add 1. And really that works on 1 as well. Like 15 minus 1 is actually 14. But we want all 15 of them. And so it's that weird thing. So you're really subtracting the top minus the bottom, but then you're also kind of adding 1. All right, so hopefully these notes help a lot. This is a little bit trickier stuff today, but it is just 3 formulas, right? We just have to pick out the right formula, and then the calculator part is a little bit tricky. So as always, class, if you need help, please make sure you ask.